Welcome, ladies and gentlemen, to our lecture on simple harmonic motion. So we've talked about a lot of different systems where things are moving around, but now I want to introduce systems where motion is repeated. So think of something like a pendulum swinging back and forth. Or think of maybe we have a star with a planet orbiting around it. Or think of if we had a mass on a spring sitting here on a frictionless surface and it was bobbing back and forth like this. In all of these cases, we have some path of motion that's repeated over and over again. So let's consider one of these cases. Let's consider the mass attached to the end of an ideal spring. So let's say the mass can slide on this frictionless surface here, and that the spring has some equilibrium length where the mass is sitting at rest. Okay? Equilibrium, remember, means that the net force is zero. So it sits at this length, and the spring applies no force to the mass, and everything just stays in equilibrium. Okay? But now imagine that I push it back a small distance, d. So the block is now, say, here. The spring is compressed. And we've displaced the block this distance, d. So we know that the spring will apply a force, right? And for a small displacement, this force obeys Hooke's law. So the force that's on the block right now, the force from the spring, is equal to minus kx. Okay? Now, if we choose this to be the positive x-hat direction, then the displacement here is minus d, and so the force is kd. And we've also learned that the spring is storing potential energy when it's like this, right? And that potential energy for the spring is 1/2 kx squared. Okay? And in this case, of course, the x is squared, so the positive and negative signs aren't important. So we have 1/2 kd squared. So that's when we have the block displaced and we're just holding it there, right? But then what happens when we let it go? Well, when we let it go, then there's a force acting on it, right? So it'll have an acceleration, and that acceleration will pull it back toward the middle. Okay, so it's going to move this way. It's going to move toward equilibrium. And we know from conservation of energy that the energy stored as potential energy in the spring is going to be converted to kinetic energy. Okay? So the block is pushed back toward this equilibrium point, gaining speed and therefore kinetic energy the whole way. And then when it gets to the equilibrium point, when it gets back to here, well, now there's no force acting on it, right? So the acceleration is 0. So Fs equals 0. But now, when it reaches equilibrium point this time, it has a velocity, right? So if it had 1/2 kd squared when we had it pulled back like this, now when it reaches here, of course the x part is 0. So it doesn't have any potential energy from the spring anymore. But conservation of energy tells us that 1/2 kd squared, the initial energy, is now equal to 1/2 mv squared, the final energy. It's all kinetic energy now, right? And so V equals k over m in a root d. Okay? So it has this velocity when it reaches this now, this equilibrium point. But then that means, even with no force acting on it, it shoots right past the equilibrium point, right? Because it has a velocity, it's moving. So then as it moves to the right and goes out here, let me draw that slightly better. Goes out here. As it's traveling out here to the right, there's a force acting on it, right? And that force is minus kx. But now the displacement is positive, so the force acts in the negative direction, slowing the block down, okay? So it has an acceleration that slows the block down. It has a deceleration. And then it goes all the way out. It has 1/2 mv squared energy at the equilibrium point, right? So now that's initial when we consider going from the equilibrium out to the right. And as it goes all the way out to the right, at the end, it has 1/2 kx squared. Okay? There's some displacement there. And that displacement is going to dictate all of the energy now. All of the energy is going to be potential energy again, because at some point out there, it's going to slow down enough that it stops, and then it's going to start coming back the other way, right? So what is x out there? X equals m over k in a root times v. But then v is equal to k over m in a root d. And so x just equals d. The same displacement that we gave it to the left when we started this whole thing. Okay? So it goes out to this displacement d, and it stops. But now there's a force acting on it, right? The force that's pushing it back toward equilibrium. So it has an acceleration. So it moves toward equilibrium, right? But then when it gets to equilibrium again, this time, it has a velocity, right? It has a velocity that's going this way. So it shoots right past equilibrium and starts going to the left. And now there's a force on it, pushing it toward equilibrium, slowing it down until it gets out and stops. At what distance? D again, right? And so we're trapped in this perpetual cycle of motion, okay? We're in this cycle where the system has energy, and that energy is constantly being transferred back and forth between kinetic and potential energies, okay? This is what we call periodic motion. And in periodic motion, we repeat the same motion over and over again. And periodic motion has some key features that we'll use to describe it all the time. Okay? So first, notice that the block is going to move back and forth, but there's a maximum distance that it's displaced. In this example, it was d, right? That's as far out as it ever got from equilibrium. And this maximum displacement from equilibrium is called the amplitude. Okay? We also have some set amount of time that it takes to complete one full cycle. Okay? And one full cycle is being in the same place in the motion with the same velocity. Okay? So, for example, it could be here on the left with 0 velocity. And so we would go all the way over and all the way back. And that's one cycle. Okay? But then as this thing's bouncing back and forth, imagine it's been bouncing for a while and we want to count one cycle. Then what if we started from the middle? Well, then it would be the time it takes to go over to the right. Okay? So we're starting when it's in the middle with a velocity that's going this way. Okay? Then it goes back, it gets to the middle again, but now the velocity is going the other way, so that's not the end of the cycle. Okay? It goes back all the way to the left, and then it comes to the middle again, right? And then at this point, it's going to be in the middle again with this same velocity going to the right. That's one full cycle, okay? So wherever we count it, you can see that it travels this full kind of distance twice for one full cycle, okay? That one full cycle is the period, just like we had for uniform circular motion. Remember when we had the star with the planet going around it, we said that one full rotation was a period? Well, that's one time through this repeated motion, right? That's one cycle of this repeated motion. That's a period. In this case, with the vibrating block, this going all the way to the right and all the way back to the left, that's one full cycle of the motion, okay? And that's one period. So then, if we describe one full cycle as the period, you can also imagine instead of doing it that way, we could describe the number of cycles per unit of time. Okay, so how many times it goes through a full cycle in a second, right? This is what we call the frequency. All right, and the frequency is always equal by definition to 1 over the period. Okay? So it has units of hertz. You remember we've discussed frequency before. We said it had units of hertz, which are 1 over seconds. And the frequency is a really common way to describe periodic motion. Okay? But then also recall that when we're dealing with uniform circular motion, 1 full circle is 2 pi radians. Okay? And in fact, 2 pi radians is the full kind of angular motion or the full cycle for any periodic motion. Okay? And so we also have something that we call the angular frequency, omega. And this is just 2 pi times f. You can see that if f is 1 over the period, then we would just be changing it from 1 over seconds. We would be putting in a 2 pi and making it radians over seconds. Okay? And this angular frequency is really commonly used because when we put something into a sine or a cosine function, which is going to come up in a little bit, we need it to be either degrees or radians, right? And degrees and radians aren't real units, okay? They're actually, they have a unit of 1, but we need it to be in this quantity to use the sine and cosine function, okay? So we have this angular frequency, and that's what we're going to see inside of sines and cosines. Now note that we used omega before for the angular velocity, but this is different, right? This is the angular frequency. So now let's go back to our example for a second. So notice that as our block moves back and forth, it always has a force that's pointed back toward equilibrium, right? That's how this spring force works. Whether it's to the left or the right, the force always points toward this equilibrium point, okay, where I have the dashed line here. We call this a restorative force, okay? It works to restore the position of the object back to equilibrium. And remember that we saw these before when we were talking about potential energy wells, right? If we had the spring here, and we had a plot, we had energy here, and we had position here, remember that the spring looks like this, right? And so we give the object some amount of energy, and then at any position along the way, it has this much potential energy and this much kinetic energy. And so remember we mentioned that a ball in the bottom of a bowl like this, if we displaced it from the equilibrium, would also have a restorative force, right? Okay? So we've seen these before. And remember that by contrast, if we had a ball on the top of a hill, if we displaced it from equilibrium here, then it would have a force that pushes it away from equilibrium, right? It wouldn't be pushed back to equilibrium. So we wouldn't get this periodic motion, okay? But even beyond the fact that the force of the spring is a restorative force, notice that the magnitude of the force applied by the spring is proportional to the displacement, right? Fs equals minus kx. So Fs gets bigger directly as x gets bigger, okay? It isn't proportional to, say, Fs equals minus some constant c x squared, right? Or x cubed or something like that, right? That's not how this works. It's directly proportional like this, okay? It's proportional to x to the power of 1. When we have a magnitude of a restorative force that's proportional to the displacement, we have simple harmonic motion. Now, simple harmonic motion might seem like a super niche case, right? I have to have a force that is proportional to the displacement, right? But it's actually really commonly the case when we have small oscillations from some equilibrium, okay? So a really large number of systems can be approximated very closely by considering them as simple harmonic motion. And generally, the requirement for us to make this approximation is that oscillations away from the equilibrium are relatively small, okay? So let's consider our example of the block on the spring in a little bit more general way. We know Fs equals minus kx, right? But instead of a spring, let's just think more generally. Okay, so what is K? K is really just the spring's resistance to being compressed. Okay, it's a constant that determines the magnitude of the restoring force. Okay, so given some displacement, the strength of the restoring force is defined by K. And then in our example, there's no other forces acting on the block, right? So if we use Newton's second law, we would say minus kx equals ma. Okay? But what's the mass? What purpose is it serving in the equation? Well, it's really just the inertia of the object, right? It's the object's resistance to this force. Okay? So we have K, some property that defines the strength of the restorative force, and we have M, the inertia that resists changes in the object's velocity. Okay? It's the thing that's resisting the restorative force. And then what we have for an equation for this simple harmonic motion is A equals minus K over M x. And remember, we're thinking of this in general. So we're thinking this could be anything, and we're kind of modeling it as a mass on a spring, regardless of what's actually happening. Okay? Now our A, well, that's really, if we think all the way back to the beginning of the class when I was describing what velocity and acceleration are to you guys. Remember, we could take the derivative of position and get velocity, and the derivative of velocity and get acceleration. So that means it's the second derivative of position that's acceleration, okay? This d squared x dt squared, this means I take the time derivative of position twice, and that gives acceleration, okay? And we know this is true. So this equation that I have left says that if I take the derivative of x twice, the time derivative, then what I'll get is minus k over m times x again, okay? This is called the differential equation. And there are whole classes about teaching you how to solve differential equations, so I'm obviously not going to teach you how to solve them here, okay? You would need a whole class to teach you how to do all these different methods for solving differential equations, okay? But I am going to tell you one method that's a lot more useful than you might think. And it's a method that works way more often than you might think it would. And it's pretty fast, especially when you've seen answers to these differential equations describing physical systems over and over again. Okay? And the method is this. Just guess the answer and then check that it works. That's it. Okay? This is actually one legitimate way to solve differential equations, okay? Just guess the answer and then make sure it works. So that's what I'm going to do with this one, okay? And if I look at this equation, I see that I need something that if I take the derivative twice, I get some constant times negative the thing that I started with, okay? So you know what works like that? Sine and cosine work like that, okay? Your book uses cosine, so I'll go ahead and use cosine. So I'm going to say that x equals a cosine root k over m t plus phi. Okay? Now, why did I guess this? Well, I guess this because I've seen lots of these things before, and I know that this is going to be the answer, okay? And you might even recognize this little guy from a really early homework that I gave you guys. I made you guys take derivatives of a function that looked just like this at the very beginning of this class, okay? So you can see if I take a derivative with respect to time, I'll get the velocity, right? And if I do that, I'll get minus a k over m in a root sine k over m in a root t plus phi. The derivative of cosine is minus sine, and I have to do the chain rule, okay? I take the derivative of the outside times the derivative of the inside. Okay, so then if I take the derivative of the velocity, the second derivative of the position, I'll get the acceleration, right? And what's that going to give me? Well, it's going to give me minus a k over m cosine k over m in a root times t plus phi. So what is that? Well, remember a cosine and this stuff inside was x, right? So a, the acceleration, equals minus k over m x, just as it's required, okay? So d squared x dt squared equals acceleration, which is equal to minus k over m x. So our guess was correct, okay? And that's it. That's one legitimate way to solve differential equations. So now let's look at this expression that I wrote for x and consider the different parts here, okay? So first I have this a out in front. And this is the only thing that's going to have units in here, so it's got to have whatever the same units that x has, okay? And we know that cosine varies between minus 1 and 1, right? With everything in between, including 0. So this x can have any value between minus a and a. And remember when we were looking at our mass on the spring vibrating back and forth, this had a particular name, right? Remember that then we had the block vibrating back and forth, and it could go anywhere from minus d to d. And this maximum magnitude that x can have, that was the amplitude, right? So the a in this equation is the amplitude of our simple harmonic motion, okay? It's the maximum distance that the particle can be displaced from equilibrium. So then let's look at the next thing. Let's look at this root k over m that I put inside of the cosine, okay? So first notice that k, remember, has units of newtons over meters, right? And m, of course, is a mass, so it has units of kilograms. And so k over m has units of kilogram meter per second squared over meter times kilogram, which is 1 over second squared, okay? And then we had a root of it, so the units of this little piece here, root k over m, has units of 1 over second, okay? Now, it's inside of a cosine, though, which means that it actually must have units of radians per second, right? Because I'm going to need to have radians inside of my cosine. So that means that what this thing actually is an angular frequency, right? K over m is a frequency. But in this equation, it must be an angular frequency because I need to have units of radians inside my cosine for the cosine function to make sense. Okay? So this is omega. And then, of course, I multiply it by t, and the seconds are canceled, and all I have left is radians. So this thing is omega, which is equal to 2 pi f, okay, which is equal to root k over m. But then, what is this last piece out here? I put this phi, this plus phi here at the end, and it didn't matter at all when I was taking derivatives, right? It didn't make any difference whatsoever. So what's it there for? Why did I include it? Well, consider my expression for x when time equals 0, okay? So at t0, at the starting point of our motion, if I don't have this phi, what I have is cosine 0, okay, which is 1, and then my x position would be a, right? X equals a. And remember, velocity, this cosine is a sine, and sine of 0 is 0. So I would have to be at a with V equals 0 to start. Okay? But I don't necessarily have to be at A to start, right? So that's when we held the block in a place and we let it go. But I don't have to start it that way. What I could have done is to have the block just at equilibrium, right? And I just bump it from one side. And then what do? It starts from 0, but I give it some velocity, right? Or I could imagine a situation where I compress it a little bit, but then instead of just letting it go, I also push it, right? So I compress it a little bit so it doesn't start from 0. X is not 0. But then I push it instead of just letting it go from rest. And so V is also not 0. Okay? And I could do this anywhere on the thing, okay? And it's going to mean that what I'm doing is I'm starting at a different point in the periodic motion, right? I'm starting from some different position along the cycle, okay? Position meaning both speed and actual position, okay? Velocity and position. So we call this a phase, okay? I'm starting at a different phase in the cycle. And so we call phi the phase angle. And phi allows me to make the starting position anything between 0 and the amplitude. And I use phi so the value of x matches whatever the starting point of my physical system actually was, okay? So then this one, phi, we call the phase angle. And phi allows us to adjust this equation to match whatever the starting point is, okay? So for any given system that had some fixed starting point, we'll just fill in phi with some angle that makes it match the physical system. So phi is just going to be some fixed addition to our periodic motion that makes everything stay in the right phase as time goes by. And notice too that if I wanted, I could make phi pi over 2, and then this cosine would become a sine, okay? So I can just as readily describe simple harmonic motion as x equals a sine omega t plus phi, okay? And then again, I'm just going to use phi to make sure that I'm at the appropriate starting position for the harmonic motion, okay? Whatever the physical system actually started at, okay? So I could write it either way, but I chose to write it with cosine just because your book wrote it with cosine, okay? And so simple harmonic motion is really common, actually. It's really very useful to us. And in general, we're going to write the position as either a sine or a cosine omega t plus some phase angle phi. Okay? Remember, omega is the angular frequency. Okay? And in our spring case, we had omega equals k over m. For simple harmonic motion in other cases where we have different restoring forces, it'll still be equal to 2 pi f, but this k over m will become something else. Okay, it'll depend on other properties of the system. But it's still going to have the same general idea where it's something that defines the strength of the restoring force, and then on the bottom, something that defines the inertia of the system. Okay, it's resistance to that force. So now let's consider a case of simple harmonic motion, okay? A specific case. Let's look, here's our equilibrium point. Let's look at a simple pendulum. And a simple pendulum is kind of an idealized pendulum. There's a mass at the end that we can treat as a point mass or a particle. And then it's on a massless string, and it swings back and forth, okay? So it swings here, up to here, and then back to here again, okay? So if we raise at some angle, theta, then recall that we'll always have gravity, mg, pulling straight down on this thing. And then if I break it into a circular coordinate system, I'd have this radial component of gravity, and this angle is theta. You can see by similar triangles, right? This is straight down, and this thing coming out makes theta. And then again, gravity is straight down, and this thing coming out makes theta again. So in circular coordinates, I'll have this direction r hat, and then I'll have perpendicular to r hat here, always perpendicular to r hat, even as the thing swings, okay, even as it goes. So the direction of this piece is always changing, but it's always perpendicular to r hat. I'll have theta hat, okay? So that's my circular coordinates. And then what I'll have here is this component. You can see I can move this component down here, and I'll have a right angle. And what I'll have is mg cos theta for this component, the radial component. And then for the component in the theta direction, I'll have mg sine theta. Okay? Now, this mg sine theta piece, that's the piece that we're going to care about. This radial piece is going to be completely canceled by the tension in the string, right? In fact, it's going to be canceled and then some, because the string is going to have to provide the centripetal force for this thing to keep moving in an arc. Okay? So that radial component is completely canceled, so it's not really very interesting to us. This component in the theta direction, though, is going to create a restorative force. When the bob is over here, it's always going to point back toward equilibrium. And again, when the bob is over here, that piece is always going to point back toward equilibrium, okay? So this component of gravity that's in the theta direction, it's always going to be pointing back toward equilibrium, which means it's a restorative force, okay? And that component is mg sine theta. So now, if we consider using Newton's second law in the theta direction, we have minus mg sine theta equals ma. So A equals G, minus G sine theta. Okay? And the arc length that this thing covers in some given amount of time, this little kind of piece of an arc that it might cover, if the length of the string is L, then that arc length is always going to be L theta. Okay? And we'll call that arc length S. And so for simple harmonic motion, we need to have something that looks like A equals minus some constant times the distance from, or the displacement from equilibrium, right? So S in this case. But that's not what we have here, right? We have A equals minus some constant times sine theta. But it turns out that if we're in radians, sine theta is approximately equal to theta, okay? And this approximation is actually really, really good out to angles that are equivalent to about 15 or 20 degrees. So we have to be in radians for this to be true. That's the units that are required for this to be true. But if we have an angle that's in units of radians that's equivalent to about a 15 or 20 degree angle, this approximation is really, really good, okay? It's actually very close. So then we can modify our equation for acceleration and say it's equal to g theta. And then using the definition of our arc length up here, we can substitute theta out, and we can say that A equals minus g over L S. And now we have that A equals minus some constant times the distance or the displacement from equilibrium. Okay? So now it does look like simple harmonic motion. And instead of k over m, we have this g over L. So this L characterizes the inertia of the pendulum as it rotates around this axis up here, right? And recall that the moment of inertia would depend on L. And this g characterizes the strength of gravity, right? So for some given displacement away from equilibrium, this G is going to give you a strength of the restoring force. Okay? So our omega is equal to root G over L. Okay? And then recall that omega is always equal to 2 pi times the frequency. Okay? And that by definition, the frequency equals 1 over the period. So then if I use all of that stuff, the period of the pendulum is equal to 2 pi times the root of L over G. Okay? And notice that the period of the pendulum doesn't depend on the mass at the end. Okay? The period gets longer the longer we make the length of the pendulum, right? But it doesn't depend on the mass. And then finally, as long as the displacement was small enough that our approximation for sine theta equals theta, so sine theta approximately theta, as long as the displacement is small enough that this is true, it doesn't actually matter how big the displacement was for the period, okay? It will take the pendulum the same amount of time to swing back and forth regardless of the size of the displacement. Now, this is true of all simple harmonic motion, okay? The restorative force is proportional to the displacement. So we get bigger forces as we increase the displacement, right? So the further out we pull the bob, the greater the force that we get, okay? And this is because, in this case, it's because this component will point more in the downward direction, okay? You can imagine as I swing the bob out, if I draw a little picture down here, when it's here, this direction doesn't point down very much at all. If it's out here, then this direction points much closer to straight down, okay? So that's why the restorative force grows as we pull the bob out, even though we know the weight of the object isn't changing as we pull the bob out, okay? In the case of the spring, the force was just getting bigger, right? The spring just pulls harder the more we stretch it, okay? But in both cases, we get bigger forces as we increase the displacement, right? But then the oscillator also has to travel a further distance when we make the amplitude bigger. So the bigger the amplitude is, we get a bigger force, but also a longer distance to travel. And in the end, these two factors balance out exactly, and the period of a simple harmonic oscillator doesn't depend on the amplitude of the motion. So now notice that as we've talked about our simple harmonic oscillators, they've always been frictionless, which has meant that they would go on forever, right? If we don't have anything to dissipate the energy, we're just in this permanent loop of converting potential energy to kinetic energy and back again, right? But we know that things in the real world don't go on forever like this. And that's because there's friction involved. And we know that friction does non-conservative work on a system and removes mechanical energy from the system. Okay? So by removing energy from the system, friction causes the amplitude of oscillations to decrease over time and eventually go back to zero. And we call this situation damped oscillations. Okay? Not dampened, damped oscillations. So imagine that we have a friction that depends on velocity. Okay, this is really common for relatively low speeds through viscous fluids. Okay, so through water or something like that. And in this situation, the forces on the oscillator become minus kx. Okay, we'll just use the spring as a stand-in right now. Minus, and then bv is the force of the friction, where b is some constant that describes the strength of the friction, okay? But then v, remember, is dx dt. Oh, not dx dx. Dx dt, okay? And that's equal to m, and then a, remember, is d squared x, dt squared. All right? So this equation looks a little different than our simple harmonic oscillator did, because now we have this extra term, right? So now when we solve the differential equation, what ends up happening is that we replace the amplitude. Remember before, our solution for the simple harmonic oscillator was x equals a cos omega t plus phi. Okay? So now what happens when we have this damped situation is that we replace this a, and a goes to some new a, okay? This is a different a, e to the minus b over 2m t. Okay? And this exponential function is an exponential decay, which looks like this in time. So if we had time on this axis, right, and x here, this piece, or well, we'll use the whole thing. This piece, a times this exponential function, is going to mean that you have a up here, and this exponential function is exponential decay, which is shaped like this. Okay, and so then on the other side, we have minus a, and we have this exponential function shaped like this. Okay? And then the rest of the function is going to be the same. So for damped oscillations, we're going to have a, e to the minus b over 2m times t, okay, cosine omega t plus phi. Okay? And so then what's going to happen in here is, so cosine will make phi equals 0. Okay, so we're going to start at the top here. Then we have these sine waves in here that go like this, okay? Because as time goes by, we have this function, which is dependent on time, which is going to make a sine wave, right? And then we have this function, which puts these exponential bounds on it. So you get this decreasing amplitude. And if you think about something that's in simple harmonic motion, okay, a swing swinging back and forth, or a spring that's bobbing up and down, this is exactly what you see, right? You have some amplitude to start, and then as time goes by, the amplitude decreases and decreases until it eventually reaches 0. Now, in this case, this omega is not this omega, okay? We're going to have a different angular frequency with the damping because we have something slowing down our oscillator all the time, right? So omega is going to be different. And this omega, this damped omega, okay, let's call it omega prime, or maybe, how about omega sub d? Okay, so this one is omega sub d. This omega sub d is going to be equal to root k over m minus b squared over m squared, like that. This thing is all based on properties of the system, right? So again, it's not going to change in time. So as this damped system slowly loses energy and goes to 0, the frequency of the oscillations don't change, right? But the amplitude does until the amplitude is 0 and we don't have oscillations anymore, okay? And note also that the stuff inside the square root here, it doesn't have to be positive, right? If b is big enough, this would be negative, all right? And when the stuff inside a root is negative, you have an imaginary number. And when you have an imaginary angular frequency, you have an overdamped system, okay? And in an overdamped system, no oscillations will occur, all right? So if this number does become imaginary, what it means is that you don't have oscillations. You're trying to create an equation for oscillations in a system that's not going to oscillate, okay? And damped oscillations are what we see in basically all cases in real macroscopic physical systems, right? But there are a lot of physical systems that are close enough to undamped that we can approximate them as simple harmonic oscillators, at least for some fixed period of time, okay? In some cases, damping hinders harmonic motion in negative ways. Okay, so for example, the reason you have to keep pushing a child on a swing is because the swing is a damped oscillator, right? If you don't push the child, the amplitude of the swing will get smaller and smaller until it stops, right? And then you have an unhappy child on your hands. In other cases, damping hinders harmonic motion in helpful ways. Okay? The suspension on your car is springs. So when you go over a bump, the car would bob up and down at some fixed frequency forever if it wasn't damped. Okay? But in your car, you also have shock absorbers. Okay? So you don't have ideal springs, so it wouldn't bob forever, but it would bob for a long time. Okay? But they put in something called shock absorbers. And shock absorbers have a little kind of plunger thing that has to move through some oil. Okay? It has to move through a viscous fluid, creating just this very type of friction, okay, of drag. And these shock absorbers provide damping to the oscillation of the springs in your suspension so that the car stops bouncing shortly after it goes over a bump, okay? So that when you go over a bump, what happens is the car does this. And usually, in fact, with car suspension, it's damped so well that you usually get something like this, and then it's over, right? It just kind of bumps once and maybe goes the other way just a little bit, and then it's over. And then you notice, as you get cars that are older and older, and these shock absorbers aren't working as well, then you get more and more of this kind of bouncing situation that you have here, where the car bobs up and down for a long time after every bump, right? So if anybody ever had an old crappy hoopty of a car, you probably went over a bump and the thing bounced for a long time afterward, right? And it bobbed like a boat for a long time. That's because the shock absorbers weren't working well, and so the system was very lightly damped, and so it bobbed for a long time. So now let's consider kind of the other side from damping. So imagine pushing someone on a swing. If the swing is hanging here, and we have the person on the swing, if I push it once, then it would start to swing a little bit, right? And so then it swings back and forth like this a little bit. But then imagine I push them once and it swings forward like this. But then as it comes back, right as it gets to the bottom, I push them again. Well, what happens? Well, I probably stop them or knock them off the swing or something like that, right? But I stop the oscillation of the system by pushing again, or at least slow it down. Okay? But now, what do I actually do when someone's on a swing if I want them to go higher? I give them a push to get them started, and then every time they swing back here, right, kind of at the max height of the swing, okay, when they're at the amplitude, and just as they start to go back down again, then I push them, right? And this is how we push someone on a swing when we want it to go higher and higher. Every time they start to go back down, we push with the motion, okay? And if I imagine that kind of pushing with the motion thing, if this is a plot of time, and this is the force that I'm applying, what it looks like is this. I push, and then they swing out, and they swing back, and they get to the top, and as they start to go again, I push again. And then they swing out, and they swing back, and then as they get to the top, they start to go down, I push again, right? And so what I end up with is this kind of periodic driving force, okay? When I plot it in time, you can see these are supposed to be equal intervals, okay? But you can see when I plot it in time, this periodic force drives an oscillation, and we call that a driving force, okay? So this driving force, in this case, in my example, it's this kind of square wave that happens, and this happens right as the person starts to go down again every time. But you can imagine my driving force doesn't have to be a square wave like that. It could also be a sine wave. Just like the motion is a sine wave, okay? Just like the periodic motion is a sine wave. So if I have a highly damped system, the periodic motion of my oscillator will match the frequency of my driving force, okay? So imagine that I have a swing and it's hanging in like maple syrup or something. Then as I push it back and forth, it's damped a lot, so it doesn't really oscillate, right? So then my driving force is just going to force. I'm just going to be basically grabbing this thing and forcing it back and forth, okay, if I have a driving force that looks like this. But when I have an oscillator that's going to oscillate on its own without a driving force, that's called its natural frequency. So if I have some pendulum, remember we said that the period of a pendulum, let's get this one out of the way. We said that the period of a pendulum is equal to 2 pi L over G in a root, right? That's the natural frequency of a pendulum. It just depends on this length L, okay, and little g. And so if my driving frequency matches my natural frequency, okay, the frequency that the thing would oscillate at if I wasn't interfering with it at all, like it does with the swing example, right? In the swing example, I'm making my driving force match the natural frequency of the swing, right? I time my force so that I push right as they start to go down. That's me matching the frequency of my driving force to the natural frequency of the swing. Then the amplitude of my oscillation will continually increase up to some theoretical maximum amplitude, okay? This is called resonance, all right? When our driving force matches the natural frequency, we call that resonance. And the maximum magnitude that the amplitude can reach is determined by the damping in the system, okay? The less damping there is, the higher the maximum possible amplitude, okay? With no damping, like none whatsoever, truly frictionless, the maximum amplitude is theoretically infinite. But in real physics system, there is always damping, right? So in addition, for real physical systems, they'll usually shake themselves apart or have some kind of catastrophic failure if the amplitude of oscillations grows too large, okay? So there's always going to be some kind of limit. You're never going to actually get infinite amplitudes. But theoretically, with no damping, you can push the amplitude until the thing shakes itself apart or breaks or the swing starts spinning all the way around the top or, whatever. You can push it to the breaking limit, okay? With damping, the amplitude for a driven oscillation is equal to F max, okay? This is for a force like this that's changing all the time. It's going to have some amplitude of the force, F max, okay? Divided by K minus M omega D, okay? This is the frequency of the driving force. So this force here, down here, has some frequency, right? And that frequency we're going to call omega D, okay? This whole thing is squared plus B squared omega D squared, okay? And this stuff on the bottom is all in a root. So this is the amplitude of oscillations when we have a damped system that's being pushed by a driven or a driving force, okay? So you can see when you look at this that this term here has will go to 0, making a maximum when omega D equals root K over M, right? You can just see that if I square that, what I'll end up with is K minus K. I'll get 0, and that's going to create a maximum for A, okay? But remember, K over M, that was omega for the system, right? That was the natural frequency of the system. So when omega D is equal to the natural frequency of the system, that's when we get this maximum, okay? And then much like the way that the amplitude of the damped system replaced A for the function in damped oscillations, right? This function for A would replace the A in our normal equation for simple harmonic oscillators, right? A cos omega t plus phi Okay? This function here would replace A for a driven system with damping. Okay? So we're going to stop this lecture here. Simple harmonic oscillators are hugely important to understanding physical systems that inhabit the world, and we can model a great number of systems by approximating them as simple harmonic oscillators. Okay? We'll expand on the idea of periodic motion in the next lecture by moving on to waves.